Hi everyone. So today I'll be talking about chapter 22, electric fields lesson 3. This is the last lesson of the topic. We will have a look at the electric potential and electric potential energy of this topic. So we will define electric potential. We'll look at the equation for electric potential and how to get to it, so how to derive it. We'll look at a capacitance equation, force distance graph as well, and how to get the work done using the area under it, and the electric potential energy and how to derive it as well. I will start with the last point first, and I will go back to it again at the end because we can work through this equation two different ways. You do need to know their derivations, and especially the derivation of the electric potential and how to derive this equation as well. So electric potential energy is quite similar to elastic potential energy. The energy stored between magnets and the energy stored when you lift objects away from the Earth's surface and so on. Just to make it a little bit more obvious, so imagine we have two positive charges. Now we know if I start pushing one positive charge towards the other positive charge, they will be repelling quite strongly, so I will have to use external energy to move it closer to each other. So all that energy that I'm giving the charges to move closer to each other is stored as electric potential energy. So all the work done is stored as electric potential energy. And obviously, once you let them go, the charges, the energy is released again. So we will continue with the definition. So we already know that work done can be calculated using force times distance, the separation between the charges in this case. We also know that force between two charged particles is given by QQ over 4 pi epsilon naught r squared. The separation between the charges is r. So if I want to calculate the elastic potential energy, instead of work done, we will be using the symbol E for elastic potential energy. Please don't get that mixed up with electric field strength, which is also represented by a capital E. It's a common mistake, and it's understandable, obviously, to make that mistake, but as long as you remember how to derive each equation, you won't make that mistake either way. So what you have when you substitute F in there and R there is the equation for the elastic potential energy, which is Q over 4 pi epsilon naught r squared times R. We cancel R because R divided by R is 1, which leaves us with 1R. So the elastic potential energy can be calculated using this equation. There is always a confusion between the two E's. Remember that in this case, E stands for elastic potential energy. Q we already defined as the charge of the capital Q is the charge of the object causing the electric field. Small q is the test charge of the other charge that experiences the effects of that field. And R is the separation from the centers of spherical charges, or the distance from the point charges. You already know the units. Since it's energy, it should be measured in joules, and we already spoke about the other quantities and their units. So elastic potential energy is simply the external energy required to completely separate two charged particles to infinity, because we define that at infinity the electric potential is 0. And I will explain what we mean by that as well when we get closer to it. So since we can have positive and negative signs, since we're going to have sometimes positive and negative charges, or positive or negative and negative, then the elastic potential energy can be negative or positive depending on what charges are involved. So if the electric potential energy, I don't know why I keep saying elastic. If the electric potential energy is negative, that means that you will require external energy to completely separate the charges. And if it's a positive or negative, it means that the energy is given out from when they're pushing away from each other to be separated to infinity. So definition is important. Also separating the symbol E is important too. Now just a very quick example on this. It says common salt is made from sodium and chloride ions. I didn't put the figure here, so this is an example question from the book. So what you have is your sodium and chloride ions. So there will be the negative and positive structure. So the separation between each pair of ions. So that's the separation. The magnitude of charge of each ion is this much. So Q and Q have that. Estimate the energy in electron volts. So we know that the charged particles have electric potential energy stored. And we need to calculate that in electron volts required to pull a pair of ions apart completely. You may ignore the effect of other ions. So we know that it's QQ over 4 pi epsilon naught R. We just simply put the values in the equation. So we have 1.6 times 10 to the minus 19 times the same thing. So I'll just write squared. 4 pi 8.85 times 10 to the minus 12 times the separation 9.4 times 10 to the minus 10, which gives us about 2 minus 2.44 times 10 to the minus 19 joules. So that's the energy that will be required. That's why it's negative. This is the energy that will be required to separate them. So the negative sign just simply means external energy is required to pull them apart. And then it wants us to calculate this in electron volts. So we already know that 1 electron volt is the same thing as the charge of 1 electron times 1 volt. Which means that it's 1.6 times 10 to the minus 19 joules. So 1 electron volt is this much. We calculated this many joules. So how much will that be in electron volts? So I just divide the number I got by 1.6 times 10 to the minus 19 joules. And that will give me about 1 minus 1.5 electron volts. So you can also see here a graphical representation of F versus R. You can see that the line is decreasing with, the force is decreasing with distance. If I were to get the area under the graph, since work done is force times distance, then the area under the graph is what gives me the work done, because we already know that that equation is a general equation of linking objects moving at a specific distance. But in this case, we replaced it with the force. There is one more way of calculating or coming up to the same equation. So this one, there's another way of proving how to get there as well, which we'll see at the very end. So we have seen electric potential energy. Now we'll talk mostly about electric potential and how we can also calculate the capacitance of one isolated sphere. We also looked at the force distance graph as well, with the work done under it as the area. Okay, so to define electric potential, it's a very important definition as well. It is the so electric potential at the point is defined as the work done per unit charge in bringing a positive charge from infinity to that point. So if we look at the diagram here, we have, if we had a point charge, a positive point charge at infinity, we need to do work against the field in order for us to move it to a specific point, let's say this point. So if I wanted to move this positive Q charge, test charge, to this point, I'll have to provide it with energy, and that's the energy per unit charge of the test charge, the positive test charge that I'm using. In this case, we can come up with a new equation. And also, if this, I hope this reminds you of the definition for the gravitational potential, which is the work done per unit mass to bring it from infinity to a specific point. So if you remember, gravitational field definitions are quite similar and adjustable to electric potential. We can also link this to another equation. So if you remember, potential difference from chapter 9 is the work done per unit charge. This leaves us with an equation of work done is, of potential difference is equal to the electric potential energy per unit charge. I'll use a lowercase q because this is the, we're talking about a positive test charge that we place there. So I can come up with my expression now for potential. We already said that E is equal to q over 4 pi epsilon naught r. So that means I have q over 4 pi epsilon naught divided by q. So the potential at a point in an electric field can be calculated using this equation. But this should also kind of remind you the potential difference that we saw in chapter 9. So we are talking about the potential at this point. If I had the potential, let's call this point A. So if I had the potential at point A and the potential at point B, I could get the difference between them, which will give me the electric potential difference between those 2 points. Before I move on, just a few things. This is the electric potential. It can be measured in volts or joules per coulomb. That's coulomb. And that's meters. Oh, sorry, I forgot the R. QQR. Forgot to add the R there. That's measured in meters. And we know that epsilon naught, the permittivity of free space, also has its own units. If you work out through the units, you figure out that they come up to either volts or joules per coulomb. Now, a very important part is, since we already defined the electric potential, we also need to make sure that through the definition, the electric potential at infinity will be 0. So electric potential at infinity will be 0 based on the actual definition. So here we have 0 potential zero potential, electric potential, and at the other points it has potential. Now this is quite well linked to electric circuits, but in a different view of how we approach the analysis of electric circuits. This has to do with more general charges that are free to move. Now this is a simple diagram showing a charged sphere, and then the potential at point B, the potential at point A. You can also see that the distances are taken from the center of the sphere because we approximate it to be a point charge at the center. So if I wanted to get the change in potential between A and B, then it should be the VA minus VB, the expressions that you get, or to be able to calculate from that. So very quick example. We have a football of diameter. So this is the diameter. If I want the radius, usually that's 11 centimeters. So 11 times 10 to the minus 2. It's covered in aluminium foil, suspended from a nylon string, and then you have a high tension supply. So you're given the voltage, which is 5,000 volts, or the electric potential, if you want to call that. Its positive electrode is used to give a positive charge to the ball. Calculate the charge stored on the ball. Treat it as a sphere. So we're treating it as a sphere because of we can treat it as a point mass, point charge. We already know that potential is equal to Q over 4 pi epsilon naught R. So I have the potential, I have R. These are all constants, so I have them as well. So I just need to rearrange for Q. So Q is 4 pi epsilon naught R times V. And when I place all the numbers in, I get 6.1 times 10 to the minus 8 coulombs. So you see here, just a list of the values, things that are related together. Remember that you have a lot of constants as well. Don't let these constants put you off. And you can solve the questions either way, whichever way you prefer. So we spoke about electric potential. And we also stated that the electric potential is 0 at infinity. We looked at the equation and how to get to it as well. And the last part that we're going to look at is the capacitance for an isolated sphere. So we're already used to talking about and calculating capacitance between two parallel plates. In this case, we're only going to look at an isolated sphere, which is basically looking at just one single plate. We need to be able to prove this equation. So derivation expected for equation of electric potential, and Q is VC. So we need to be able to derive quite a few of these equations, especially this one as well. So we already know that capacitors store charge by collecting it on the plates. There's an insulator in the middle that doesn't allow charge to flow through. So capacitors store charge with two plates. Now, if we look at a sphere that's isolated, meaning that it's insulated from any way of the charge escaping. So if I had the charged sphere that had an overall negative charge built around it, on the surface, then I can treat this as a single plate capacitor. We can assume that, we already know that capacitance can be calculated by charge per unit potential difference. But we also know that potential difference, the electric potential can be calculated using Q over 4 pi epsilon naught R. So basically, we can use this equation to come up with an expression of the charge that's stored on the surface of the sphere, where the surface of the sphere will be this distance from the center. So remember, we can approximate a sphere to be a charged sphere to be a point charge from its center. So in this case, this little r can be taken as the radius of the single isolated sphere. I'm just going to rearrange, actually let me rewrite the expression, Q over 4 pi epsilon naught R. Now I can rearrange this for Q, since I can calculate how much charge it has stored on it. So it'll be 4 pi epsilon naught R times the electric potential. So I have equation 1 and equation 2. I can substitute equation 2 into 1, where Q is. So that will be C is equal to 4 pi epsilon naught RV over the potential. We cancel the potential, so the charge stored around a charged sphere, the capacitance of a charged sphere solely relies only on the radius of that sphere. Everything else is constant. So capacitance is directly proportional to the radius of a charged isolated sphere. So this only refers to just an isolated sphere. So you need to be able to derive this too. Okay, so a very simple question could be, what is the capacitance of an isolated spherical capacitor of radius 35 centimeters. So in this case, we only need the radius. We know that we can use this equation. So capacitance is 4 pi times 8.85 for the permittivity of free space, epsilon naught, times 0.35, which should give us 3.89 times 10 to the minus 11, or more better, because we're given the answer to two significant, well, the question gives us the two significant figures, the values, with 3.9 times 10 to the minus 11 farads. So going back to the learning objectives, we have completed all of them. We have also shown all the derivation of all the equations. Just make sure that you don't mix E for electric potential energy with E for electric field strength. And be careful with the units and everything that you label and the definitions. If you do have any questions, write them down and you can ask me in class.